Welcome to all of you watching, streaming, or catch up. It's a great pleasure, I would say, to be back in Oxford where I studied. Of course, it was in a different building in those days, but I have been in this building a number of times before, and it's a great honour and privilege to give this lecture today. So I slightly changed the title. I wanted to call it On the Millennium Bridge Synchronisation Myth. And the subtitle is Why Pedestrian Bridges Wobble, Synchronisation and the Wisdom of the Crowd. And here the wisdom of the crowd refers to how crowds behave on moving structures and how crowds behave generally, but also how the wisdom of the crowd can sometimes, in my view, lead to scientific theories and something that, inverted commas, everybody knows, don't they, that might not be true or might not be as simple as that. And I should say at the outset, this is work with my colleague John MacDonald in civil engineering and his former PhD student Matt Bossian, who's now at the University of Leicester, and also Igor Belik, Russell Jeter and Kevin Daly, who are in Georgia State University. So you may have seen, I don't know, 20 years ago it is now, almost 20 years ago, you may have seen videos, or you may have been present, of what happened on so-called London Millennium Bridge. Now, the London Millennium Bridge was built as the world's first horizontally suspended suspension bridge. And it was, it links the Tate Modern Gallery with St. Paul's Cathedral. It's an iconic structure, and it was billed as, it won awards because of its unique heritage or its unique design as a collaboration between an architect and an engineer. But on the day it opened, this happened.
The Millennium Bridge is a stunning aluminium and steel structure. A bit of great design
and engineering. This is a BBC programme. All my videos are nicked off the internet, I should say that.
On opening day, 10th of June 2000. But as soon as the crowds hit the bridge, there was a problem. It wobbled. And not just a bit, but enough to make people cling to the handrails for security. Clearly, the crowds themselves were driving the bridge in a completely unexpected and very worrying way. The bridge was closed 3 days later and has remained closed ever since. But how could this have happened? Why wasn't it?
So how did it happen? Well, I want to go back into, so the popular theory, roughly speaking, is when you look at that video, I don't know what you saw, but you might have seen a whole lot of heads that appeared to be moving in synchrony. And there's a strong belief that what happened was that as people started to synchronize their footsteps, so the bridge started to have its natural frequency amplified. And as its frequency was amplified, so the synchrony increased. And this is used as almost, I would say, a sort of a billboard poster or a canonical example of the mathematical theory of synchronization. It was very convenient because the year 2000 was when that theory was really taking off. So I want to tell you about the mathematical theory of synchronization. And it goes back to Christian Huygens, who until Didcot Parkway Station, I didn't realize had two A's in his Christian name, but as always, I've been preparing these slides right at the last minute, and so-called Huygens clocks. Then there are lots of other examples of synchrony, and if what I'm saying is boring or not interesting, you can look at these cats and decide whether they are synchronizing or not. Also, brain waves, power grids. Our power grids rely on the idea that the whole of the AC circuit that supplies power to the whole of a single grid, like the nation, is completely in synchrony. So you know that AC circuit is essentially, well, you can think of it as a wave vector of polarized electromagnetic radiation, but that has to be completely in sync across the whole network, otherwise it goes down. And rhythmic clapping. Well, how does that come about? We'll talk about that. Then I want to talk about Yoshiki Kuramoto, who came up with a really simple mathematical theory of synchronization, which I will show you. At least I will do a bit of maths on the board and then give you a hint at how you can go from two to many oscillations and then give you the explanation for the London Millennium Bridge. But really this is going to be a tale of two bridges, because there's another theory of how the London Millennium Bridge and other footbridges might go unstable. And I might call that theory, how not to fall over. It's quite a simple theory. It's a bit like Douglas Adams' How to Fly, which is aim for the ground and then miss. And this was actually triggered, amongst other things, by my colleague John MacDonald's observation on another iconic bridge, the Bristol Clifton Suspension Bridge, and I'll explain to you his model of walking and the idea of so-called negative damping, averagely speaking. And then simulating and some results from three simple models, and then ask what is the right answer. And perhaps that's always a difficult question when you're doing maths of the real world. There is no such thing as a perfect answer when you're doing maths of the real world. And I might give some philosophical remarks, or I might run out of time. I certainly will run out of time, because as I was telling Dyrol earlier, who runs these, my general way that I give lectures, and I get student feedback that says, enthusiastic, yes, 5 out of 5. Did we understand it all? Can we follow it for the exam? Yeah, you didn't. What was the best thing about Professor Champneys' lecture? The first time he told the joke. What was the worst thing about his lecture? The 6th time he told the joke. So I tend to prepare meticulously and then say the first thing that comes into my head. So I'll almost certainly go over time, for which apologies, but I will speed up. So Christian Huygens was a sort of contemporary of Newton, and he's a physicist, a mathematician, but also an inventor. And he discovered by chance an unexpected or odd sympathy that he observed at home. And here's a diagram of what he had. He had 2 pendulum clocks suspended on a rack between 2 shelves. And people have done modern versions of this. So these are not pendulum clocks, these are metronomes. They're not quite tuned to the same frequency, and they're not in sync. And what we're now going to do is we're going to couple them, or this physicist is going to couple them, this YouTuber is going to couple them, by putting them on a plank, rather like I have there, and watch what happens, or listen to what happens. Just the tiny coupling between the pendulums by the fact that they are all uniformly contributing to the same sway of this plank, that they're all coupled together through the vibration of the plank, causes them all to fall into sync and the plank to start to move. Oh, no, I didn't want to do that. Thank you. And in fact, this idea of synchrony has been observed in many other situations in the physical world. So this is a picture, this isn't a video because I couldn't find it, of that I took in the gift shop of the Great Wall of China. I've only been to China twice. This was the first time. And there was the conferences in Beijing, and there's the obligatory afternoon expedition to the Great Wall, but it tipped down. Frankly, it was absolutely pouring. I'm doing my best not to swear. I very nearly said a rude word, but it was raining cats and dogs. Fortunately, it cleared up and we did get to go on the Great Wall. But there was about 10 or 15 of us, mathematicians and physicists, who became fascinated by this display of waving cats. And you might be able to see it in this still here. You might just be able to see it. Sorry, there's a pointer. You might just be able to see that if you look at each row is in sync with each other. This row here is they're all in sync with each other. This row here is approximately in sync, and this row here is approximately in sync. And we started playing games of, what if we take one of the cats out? What if we move one of the cats so that it moves its arm? What if we swap and turn them backwards, etc.? Great fun for mathematicians and physicists, probably of no relevance whatsoever. These are fireflies. And after a while, towards the end of that clip, I hope you can see that they're beginning to synchronize. It's hard to find, here. After a while, when there's a sufficient density of them, they start to synchronize. This is what happens in power grids. So this is an example of 2 electrical generators that are being driven at slightly different speeds, slightly different voltages, and then an electrical coupling between them is switched on. And watch what happens. So these are 2 different electrical generators. So there's a strobe on this. I should have given a trigger warning. I'm very sorry. Look away if strobes are a problem, but it's not the whole room, it's just the video. So he's now going to switch on an electrical coupling. They're just sharing, they're just going to be part of the same circuit. And being part of the same circuit is going to be enough when he switches on that coupling. Now, he hasn't changed the drive to either machine, but they synchronize to the common rotation frequency and the common phase. It's just a weak electrical coupling between them. Oops, we go back. And this is a video of an audience clapping. How does that happen? Was there somebody, a conductor, there wasn't, on the stage going, now, 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 now. So not only did they all hit the same frequency, but they all hit the same frequency and the same phase. In fact, there has been a very interesting study recently of somebody looking at this, and they discovered one of the things that you might notice about the two halves of that clip. I'll show it again. It's hard to see this because you're seeing the collective clapping in the beginning. But actually, it's hard to synchronize your clapping if you clap too quickly. Generally, clapping is liable to be synchronized if you start to clap more slowly. And they discovered in communist countries that when there was a fantastic speech that everyone enjoyed, there was a lot of clapping. When the dear leader gave a speech that they were obliged to clap, suddenly there was synchrony. Now, you draw your own conclusions about why that might be. But listen to this again. Just watch an individual. They're clapping quite quickly. Quite enthusiastically, slightly less enthusiastic, and it slows down into synchrony. That's interesting. I don't quite know why. So what am I going to talk about? Well, as I was sort of intimating there, there's two ways you can make independent oscillatory things oscillate. There's the orchestra kind of way. Orchestras are in sync because there's a conductor. There's a conductor who says, now everybody make the same down string on your bow. Or for the violinist, there's a leader of the orchestra. There's a follow my leader. But there's also a spontaneous synchronization like you might get in an ensemble piece. And I'm going to talk about this spontaneous kind of synchronization because there was certainly nobody on the Millennium Bridge. You do get synchronization, by the way, when you play music. Another way of getting synchronous clapping is during rock concerts. And in fact, there can be problems when rock concerts are played in sports stadia, because sports stadia are designed to take a certain weight of crowd. What they're not designed to take is a certain weight of crowd who are all doing this at the same time in the stands. And there have been examples where huge instabilities have been set up due to orchestrated synchronous jumping. So the spontaneous case are the fireflies. There's nobody telling the fireflies when to turn off. There's nobody telling you when to clap. The metronomes, there was nothing to tell the metronome which phase to choose. And these waving cats that may or may not be synchronizing, there's nothing to tell them what phase to take. And there's a fundamental theory due to Kuramoto of phase-coupled oscillators. And his very clever idea is consider n. Mathematicians like to call things n or epsilon or whatever. So n is some large number, large being 2 or more. That's a private joke. But then imagine that they're coupled in some way. Perhaps they're all-to-all coupled, but weakly. And I'm not going to say what weak means. I'm going to deliberately say I'm not going to say what coupling is. But they're all things that want to oscillate. And they want to oscillate, and I don't care how they oscillate, whether it's backwards and forwards, or whether it's round and round, but I'm going to describe their oscillation by its phase. In other words, its fraction of a period. So I'm going to throw away all the physics of simple harmonic motion or whatever, and I'm going to suppose that these are things that are naturally oscillating. So I can represent that motion in some sense as a circle of phase. I go from 0 round to 360 degrees, etc. And so how we might write that mathematically is I describe this phase variable phi, or phi I, and d phi I dt, Newton invented this dot notation for rate of change. That means the rate of change is just omega. What's omega? Omega is a frequency. So in other words, I'm just something that is constantly changing my phase at a constant speed omega, and then going back again and starting again. So I'm going round and round, if you like, at a constant speed. And then I'm going to suppose that I'm listening in some sense. And I don't know how that listening is working. It may be listening through my ears, it may be listening through the vibrations in the plank, it may be magnetic with those cats, I'm not sure. It may be through current and voltage, but it's kind of weak. There's some weakness that says, if my neighbour, or something that I'm coupled to, has a different phase to me, I'm going to adjust. There's some feedback that says if we're not in the same phase, I'm going to sense that. Now, I don't know what that feedback is. It's some function. I'm just going to call it F. And there's some coupling strength, kappa, which is this weakness. So if you look at these cats, the phase is how far through the cycle of backwards and forwards I am, and kappa is the extent to which I'm being influenced by one of my neighbouring cats or one of the further away cats. So these are the small couplings, and they're typically very much less than 1. And if you think about it hard enough, you realise that this only makes sense in this phase-coupled sense if the function f is symmetric, if it's 2 pi periodic, and I assume that if there's no phase difference, then these things are just happy to oscillate, so f of 0 is 0. And you realise the simplest functions that do that are just simple sine waves. So a simplest thing you can take, if you know about how to decompose functions that are, or signals that are periodic into sine waves, you would say you take a one-mode Fourier truncation. You just take the simplest possible function. You just take the simplest possible law. I don't care what it is. I'm just going to take the first term in some expansion, and that turns out to be a sine wave. What is a sine wave? Sine in here is just a sine wave is just something that does this. This is sine of phi from 0 up to 360 degrees as a function of phi. So I'm just going to assume that I have these weakly coupled oscillators, and in the case of all-to-all coupling, where the coupling strength is the same, then Kuramoto first wrote down these equations, and you can do really interesting things with these equations. What you find, I'm going to do a bit of maths, you're going to do a bit of maths with me, I hope. Let's take the case of n is 2. Okay, so I'm going to take 2 oscillators. And I'm going to assume that this kappa is just some constant, and on the previous slide I had a kappa over n just to give you some scaling, but that's not strictly necessary. So in fact this kappa is kappa over 2 from the previous slide. Whoops, sorry. In fact it's 2 kappa. No, it isn't, it's kappa over 2. Oh, sod it, Alan, shut up. Sorry, I didn't say that out loud, did I? No, I'm glad. Phew. And let delta omega be the difference between these two frequencies. So these are these two generators that are going round. Phi is the angle of that generator, and they're going round at very slightly different speeds. And now let me take the difference. Let me take the difference, and I'm just going to subtract these two equations. If I just subtract these two equations, I get the following. After a tiny bit of algebra, I find that the difference between them, the psi dot, so that's phi 1 minus phi 2. If I subtract these two equations, I find that this psi dot is just the difference in the omegas minus 2 times kappa of psi. Then for this equation, I can prove some things. I can prove to you that if the coupling strength is large enough and the frequency difference is small enough, then this equation has 2 different equilibria. That is 2 different constant phase solutions, where both the constant phase difference solution, where the 2 oscillators will be in phase. And this is really easy to show, because let me look at that equation. What does it say? It says phi dot, which is a rate. Phi dot is the rate of change of phi. As a function of phi is delta omega. Let me assume delta omega is positive. It doesn't have to be. So that's the difference in these two frequencies. That's fairly small. Minus something, 2 kappa times sine of phi. Well, sine is a graph that I had previously, So that's going to be a function that looks something like this. And there's my 360 degrees, and there's my 0 degrees. And that's badly drawn because this here should be at 2 kappa, careful, minus delta omega. What have I done wrong? This is totally rubbish. This should go up like this, that should be a 0 point, this should be a 0 point, and I should come back to there, and that should be my 360 degrees. But notice what this does. If this 2 kappa minus delta omega, as I've drawn it, is less than 1, if that down there is less than 1, then I have 2 zero crossings. What happens at these zero crossings? Well, this graph tells me everything. Because if this is my angle phi, this graph tells me whether phi varies positively or phi varies negatively. So here d phi dt is positive, which means if I start here, I go this way. I increase my phase difference. But if in this region, d phi dt, the rate of change of phi, or phi dot, is negative, so I go this way, and I end up here. And similarly, if I start in this region, because d phi dt is positive, I go this way, and I'm going to end up here. And I go right round, 360 degrees becomes 0 degrees again, and I'll end up here. But see what that does? That shows me not only are there 2 zero crossings, fixed points, points at which phi doesn't change, the rate of change of phi is 0, it shows me that this one is stable. Because if I start slightly to the right of it, I pop back. If I start slightly to the left, I pop back. And this one is unstable. If I start this side of it, I go all the way around the world and come back to here. And if I start this side of it, I come back to here. That's Dynamical Systems 101. We have done a stability analysis of a dynamical system just by looking at whether something is positive or negative. And that shows me that there is a state, and we call this the synchronous state, where the difference in phi is small, it's close to 0, and it's constant. And this, provided this delta omega divided by 2k is less than 1, if everything is positive, so provided if this condition here is true, then I'm going to tend to this in-phase equilibrium rather than the out-of-phase one, and that's going to be stable. Now you can generalize that analysis. That was an analysis with just 2 oscillators. If I have many, for simplicity, let's suppose everybody interacts with everybody else, then you can do some things statistically. You can write down what's called a master equation. You can assume that the whole ensemble of all of these things, on average, you can add together how they oscillate, and you can say that if you look at how something oscillates and you look at its x component, so if I think of something that's going round in a circle and I look at it from the side, then it goes up and down like a sine wave. And if I look at it from the top, then it goes backwards and forwards like a cosine wave, which is the same as sine but just shifted by 90 degrees. And that tells me that I can define, if I average everything, don't worry about this I, that just means am I looking from the top or from the side effectively. But there's a neat way of writing that, which is called Euler's formula, that we don't need to worry about. But essentially I can do some averaging and say, on average, I can think of this as a big oscillator multiplied by something that's going round a circle. And depending on whether that average is, if that average is 1, that tells me that everything is in synchrony. If that average is 0, it tells me that they're all over the place. That there is no synchrony at all. And this is called an order parameter. And Kuramoto invented this order parameter that says how much of this is in synchrony and how much is it not in synchrony. And more recently, people have been interested in what happens in the boundary between synchrony and non-synchrony, in the case where the coupling strength is not really large enough to cause complete synchrony, but it's not 0. There is some coupling. And these have been called chimera states. Chimeras are supposed to be creatures that are composed of two different organisms, like a lion with a donkey's head or something. And the idea is you can have these oscillators, some of which want to synchronize and some don't. So here are some simulations, again just pilfered off the web, of the case when the coupling strength is large enough and the case where it isn't. So in this simulation on the left, there's just a whole load of coupled oscillators, and we're representing their phase, the degree of how far round they've gone. And in this case, it's for purely illustrative reasons. They're not all represented on a circle, but so that you can see them all, they're pulled out transversely to the circle. So some of them are further away and some of them are nearer in. That's purely for illustration. So if you take some that are starting in random position, as you allow them to oscillate, so they start to swarm together and very quickly all start to oscillate with the same phase. So this would be a case where the coupling strength divided by the phase difference is large enough to cause all these oscillators to fall into sync. And here is a case where that's not, oh, sorry about the music. There's a case, and you can watch this for hours, where the coupling strength isn't quite large enough, but you see this patch of fairly synchronous behavior. These oscillators are trying approximately to follow each other. Now, I told you that when I was at the Great Wall of China, myself and some other delegates of this conference found these waving cats that were perfectly in synchrony. Unfortunately, this weekend when I went and bought these cats and thought, yeah, I know what I'll do. I'll put them on the... Oh. But then I realized what these guys are doing is really interesting. They're not synchronizing, but they are interacting with each other. What seems to happen, if we look at this guy in the middle, guy being a gender-neutral term, he speeds up and slows down. Now, large amplitude, and then as he slows down, the next one gains a large amplitude. As he slows down, the next one does. Bounces back, then this one's got large amplitude, then this one's got large amplitude, then this one's got large amplitude. There's a traveling wave going on. And this is one of the things oscillators can do. If they don't have enough coupling strength to cause them to fall into synchrony, you get this traveling wave of behavior of large and small amplitude. And that seems to be what's happening in the experiment that I tried to do. So, what has this got to do with bridges? Well, the accepted, if you like, the textbook example of synchronization and the Millennium Bridge, the explanation goes as follows. You think of the bridge as having a lot of pedestrians, and each of the pedestrians are approximately trying to walk at the same frequency. Approximately. But as the bridge just slightly moves, just those slight movements of the bridge is enough to push them more towards synchrony, and that synchrony is enough to then start to make the bridge move, that then is enough to start to couple everything together. And that's essentially what this video shows with metronomes. If I take enough metronomes and put them on this again, nicked off the internet, and take a large bridge-like structure, eventually almost like soldiers moving with military precision, the fact that they're all coupled through the collective motion of the bridge is enough to make them slowly fall into approximate synchronization. Left, right, left, right, left, right, left, right. Company, halt! Etc. So the full explanation goes something like this. This was the world's first horizontally suspended bridge. Bridges are designed generally to be vertically suspended. Suspension bridges have cables that come from above. And a lot of effort goes into making sure that there aren't resonant frequencies in the vertical vibrations. And for example, it's been known for a long time, there's a command amongst troops to break step when walking across a bridge. Because if troops were to march across a bridge all in sync with each other, it was known that that caused large vertical vibrations of the bridge. So it was believed that as long as it wasn't soldiers marching, that pedestrians, all of whom have random phases and walk randomly across a bridge, were never likely to cause a bridge to go unstable. And so it seems they don't in the vertical domain, but they appear to in the horizontal domain. So if you take a bridge that has a horizontal elasticity, and this one had a very large one because it was horizontally suspended approximately, then this synchronization of footsteps, given sufficient numbers, was enough to cause synchrony and therefore an instability. And it doesn't really matter, so this theory goes, how you model the pedestrians, because they're all oscillators, and Kuramoto's theory just relies on phase coupling. It doesn't rely on the particular details of the oscillators, and it looks a bit like having a lot of Huygens clocks or Huygens metronomes. And this is the paradigmic, I can never say that word, it's a paradigm example of synchronization. For example, have a look at the book Sync. It's an excellent book in Steve Strogatz's book in Penguin. And only about a month ago, I heard Hannah Fry, who's also superb, on Six Music in the morning, talking about synchronization and using the London Millennium Bridge example as a classic example of synchronization in the real world. Actually, the engineers Arup were called in to re-engineer the bridge. The bridge was closed for 2 years. And what they did is they made empirical observations. They didn't understand all this theory of synchronization. They just made empirical observations. And they noticed that on average, a pedestrian provides some lateral force. And that force appears as damping, but it appears as damping with a negative sign. So they said, we can think of each pedestrian as like a negative damper, whatever that means. And they drew a straight line. They actually got their employees and volunteers to walk across the bridge when it was closed and took all this data and drew a straight line through it and found that there is a negative damping coefficient, whatever that means. And what they concluded was the way to solve this problem is stick ugly, whacking great dampers on the bridge. Stupid engineers didn't understand the theory. That's kind of not what anyone's ever said, but what mathematicians and physicists sometimes think. I can remember being told as an undergrad on a maths degree, come on, think, you're thinking like an engineer, as if that was kind of empirical and not deep enough. But if you look at, this was also from last year, another fantastic lecturer, Matt Parker. He describes himself as a stand-up mathematician. If you've ever seen him, you'll know what I mean, but if you haven't, I strongly recommend seeing one of Matt Parker's lectures. This is just last year in the Royal Institution, and a lecture entitled When Mathematicians Get It Wrong, and describing how the engineers got it wrong because they didn't understand synchronization. This is just one of his preliminary examples.
You've got the Millennium Bridge in London. This was opened in the year 2000, and it was only open for a couple of days before they had to close it. They looked at the footage. Now, if everyone's walking randomly, it should be fine, because they're not all going to match one particular frequency. But they looked at the footage. About 20% of the pedestrians, admittedly it's quite crowded, but 20% of them were all marching in sync. The bridge is moving about 7.5 centimeters either way.
Only 20% of the pedestrians, under the best estimation, were walking in sync. Actually, if you study those videos, it's absolutely clear that quite a few of the heads are moving from side to side. I have never seen any video, personally, that has suggested any synchronization in where they're actually placing their feet. If you looked at some of those earlier videos, you might have seen some school children who are sort of placing their feet kind of like this as the bridge is moving. There's certainly no evidence that I've seen of people placing their footsteps in synchrony with the bridge. It's also not a good example of Huygens clocks or these cats, because the bridge has a natural frequency. The common frequency that these pedestrians adopted under this explanation is not some random frequency or some collective frequency, the average frequency of the pedestrians, like it would be in the Kuramoto theory, but it is the natural frequency of the mode of vibration of the bridge. And also, if that's the right explanation, how do you explain what Arup observed and is widely agreed, that there needs to be a critical number of pedestrians for this to occur? Why is it when you have one less pedestrian than this critical number, they don't synchronize and there isn't an instability? But when you have one more, it kicks off. Not understood. Pedestrian footsteps are nothing like simple sinusoidal oscillators. We walk in a very strange way. Essentially, we walk on flat ground with expending almost no energy. What we essentially do is we fall over. We balance on this leg, and we fall over onto the next leg. And then we swing this leg through, and we fall over. That is nothing like a pendulum or a spinning generator. And why did the Arup negative damping explanation work? Can lateral instability on bridges, how do you explain instabilities if the bridge isn't tuned to the pedestrian natural frequency? Is it very special for this London Millennium Bridge, as some people claim, that it just happened that they picked a vibration, or they picked a suspension mechanism that meant that the mode of vibration of the bridge was very close to a natural pedestrian frequency? Unfortunately, that's not the case. And one of the reasons we know that's not the case is if you dig into the literature, there have been many examples of bridges, not just the Millennium Bridge, that have gone unstable due to crowds walking on them. Not due to traffic, but due to crowds. The Auckland Harbour Bridge doing a particular Maori protest walk. Footbridge in Changi Airport in Singapore. And then in Bristol Suspension Bridge, it was observed. So if you know anything about Bristol, the suspension bridge goes across a gorge which connects the city to Ashton Gate Park. And every summer there's Europe's largest balloon festival in the park. And in 2 of those evenings they have a night glow event. And what they do is they get a massive arena and about 100 balloons get lit up. And lots of novelty balloons get lit up. There's massive festivities, etc. And it finishes at 10 o'clock and everyone walks home. Now the quickest way to walk home is across the suspension bridge. And they would close it to traffic as well, so that you only get people walking across it. And then it was noted that the bridge started to move. So my colleague John MacDonald was called in, and the following year he instrumented the bridge. And this is what he found. What I'm showing you here is, this is over the course of the week, and these are the peak lateral vibrations just after the night glow event. So these are what the RMS, so the average displacement, daytime, evening, and then the night glow event, massive in the lateral direction, not in the vertical or the torsion. And if you look in more detail, you can actually look at the record during the time the pedestrians were walking across. But what was noticed is that as the number of pedestrians changed, there appeared to be a critical number beyond which, I don't know if you can see this in the blue and the red here, that 2 different modes of the suspension bridge were excited. So it wasn't just that the pedestrians happened to be walking at a certain frequency, which was the mode of the bridge. The pedestrian average frequency was actually halfway between 2 different modes, one of which, if you like, is like this, and the other of which was like that. And both were excited. How can that be synchrony? How can you get simultaneous synchronization to 2 different vibration frequencies? There's something odd about that. So what about Arup's negative damping idea? Well, here's a really simple, non-constructive explanation of their idea. And I think they hit the nail on the head. Have you ever considered what you do when you're walking on ground that is moving laterally? And if you've never experienced this, you're probably lucky. There are some people in the audience, there are some experiments that can be done by adults that involve, how can I put this, a certain change in their perception due to circular liquid intake that makes them perceive that the ground is moving. And if you've ever witnessed, don't try this at home, children, please. If you've ever witnessed somebody undertaking one of those experiments, they tend to walk in a way that is a bit sort of like this, as they're changing their balance all the time as the ground seems to move away from them and doesn't seem to be very flat. But seriously, what are you doing? What are you doing if you are moving? If you're on ground that's moving, perhaps, I don't know, at a theme park or something, sometimes you step onto those rotating platforms. If ever you walk on ground that's moving, what you desperately try and do is not fall over. And how do you not fall over? Well, if I've got some momentum in this direction, I'm going to ensure that my next footstep loses that momentum. I'm going to try and right myself to decrease the amplitude of my oscillation. So whatever is causing me to oscillate, I don't care about the ground, I don't care about necessarily where I'm headed, although in a rough sense I might. What I care about is not falling over. And therefore I want to lose energy from this degree of freedom. I want to decrease that energy. And where do I want to put that energy? Well, there's two places I can put it. I can warm my muscles up, or I can give it to the ground. I can push against the ground. And that's generally what we do when we walk. That's where we get extra momentum from when we run, etc. We do work against the ground. So if I want to not fall over in that direction, I'm going to push against the ground. And the only place that energy is going to go is into the ground itself. Now, normally the ground is very stiff and it can take it. You know, it might get impacted or whatever. But if you're on something like a suspension bridge, on average, what you're doing is, if it starts to move, is you're going to give energy to the bridge. That's irrespective of whatever speed you're walking at. And whatever speed the ground is moving, on average, whenever you start to wobble, you're going to give energy to the bridge. And that's essentially what negative damping is. It's the coefficient, it's the degree to which, on average, a pedestrian wants to give energy to the bridge if you cause the pedestrian to move. And therefore, if you get enough pedestrians, then they get enough of this negative damping to overcome the natural bridge dynamics, the natural damping of the bridge, and the thing will go unstable. And in fact, this is not a mysterious thing. This is completely analogous to a flutter instability in aerospace engineering. In aerospace engineering, if you have the wind blow fast enough over a wing, or indeed the Tacoma-Narrows Bridge did something similar, where there was enough vortex shedding that caused the natural dynamics to be negatively damped, and that gives rise to a flutter instability. This is also known as a Hopf bifurcation in mathematics. And it doesn't require any matching of frequencies or any synchronization. But how to estimate this negative damping coefficient and this critical number of pedestrians? So I could show you another video, but I probably won't because I couldn't edit it very well. But what you can do is you can start to say, well, what actually happens when you walk? And basically, what you need to understand is that there's a difference between the frequency with which you're putting your feet down and the frequency with which you're wobbling from side to side. Those are completely independent degrees of freedom. And you can have a model for telling you when you put your foot down, and sometimes the central pattern generator has decided, I'm going to walk at this pace unless the ground stops me from doing so. But if I'm walking at this pace and the ground starts to move, then I might not change my pace. I might do a little bit, but I might adjust where I put my feet. And that's a different motion. The side-to-side motion is a different motion from the pattern generator that's telling me when to put my foot down. They're going to be coupled. And so for simplicity, we could imagine that I'm trying to walk at a certain speed. That's in the so-called sagittal plane, the fore-aft plane. And I'm moving from side to side as this lateral oscillating structure is causing me to do so in the so-called frontal plane. And that you can describe via various models of pendula falling onto another pendulum as I fall onto the other foot. And you can get various time series. So they're upside down pendulums rather than pendulums the right way up. And you can write down equations for these, and I won't go into it, but there's a number of different equations. John McDonnell's original model just assumes that this is prescribed. So I'm walking at a certain pace and nothing will change that. Then you can look at a model that allows that to be adapted such that if I have to take a wider step, then I'm going to adjust how far forwards and when I put the foot down. So it's just a geometric adjustment corresponding to how wide my leg is. And the adjustment is due to a sort of control law that says I'm going to try not to fall over. And then there's another model that Igor Belik and his student came up with, which just says I will put my foot down whenever I feel myself going over the 45 degrees, then I'll switch onto the other foot. 90 degrees, 180 degrees. As soon as I feel myself passing through this, I'll put my foot down. So we tried all three models. There are more complicated models. There are models of articulated legs. There are models that fully couple everything. There are models that have multiple degrees of freedom, that add masses for the legs as well as mass for the core. There are models that contain the central pattern generator as part of them. But in essence, all models of walking have this notion of I put my weight on one foot, then I lift it, and I put my weight on the other foot. And what we found, so we then did some mathematical analysis, and the mathematical analysis is model independent. It says, as long as my model is like that, I've got a bridge, linear oscillator with a massive mass, just goes back and forwards depending on how it's forced, and I've got pedestrians, much less mass, that provide feedback to the bridge, and the bridge provides feedback to them. And then what we found was that you can calculate from any model the degree of negative damping. And it contains three components, and I've called them sigma 1, sigma 2, and sigma 3. So in the simple John McDonald model, it's actually the Bossian et al. Model, sigma 1 is the only thing that occurs, which is the dependence of the average lateral force on the bridge's velocity. So if the bridge moves a bit faster, then I put my foot out wider. This diagram sort of explains where the asymmetry comes from, because you might think that on average, this notion of me putting my foot out less wide or wider to stop myself falling over would balance. In other words, the number of times I push the bridge in the direction it's already going will be the same as the number of times I push the bridge the other way. But it isn't, and it isn't for the following reason. If I push the bridge in the direction that it's already going, I put my leg down, and as my leg moves, so this angle increases, and I give a higher component of force in that direction. If I put my leg down here and the bridge is moving towards me, so that causes my foot to go that way, and I put less force. My force is now going downwards. There is now no component of force in that direction. And so you see there's a fundamental difference between doing that and doing that. So you see when people are walking on, they sometimes do this business, that provides much less energy than if you do that and end up putting your foot out wide and pushing the bridge in the same direction. And that's where the fundamental asymmetry in this negative damping comes from. And then there's an adjustment in where you put your foot, and then there's an adjustment in where you put your foot forwards and backwards as well. And then we run all three models and we found the same sort of thing. So what am I showing here? And I've almost finished. So this is I'm going to show you what happens as we do a simulation, then add another pedestrian, then do a simulation, then add another pedestrian, then do a simulation. So up to about 200 pedestrians in this particular model, we take the pedestrians to all have a similar frequency with a randomly assigned frequency and phase with just a 5% variance. And the pedestrians, this is their amplitude here, doesn't change much depending on whether the bridge is stable or unstable. But what you see is the bridge motion here, and as soon as you pass 200 pedestrians, then the bridge motion takes off, and in this model there is nothing to stop it. Now, two things you notice. One is the negative damping coefficient. The damping coefficient of all the pedestrians minus that of the bridge, it changes sign at this 200. And the amplitude starts to grow. And this here, R, is the Kuramoto order parameter. Do you remember what that was? That was the degree of how much the oscillators are in sync with each other. And in this case, there's no difference between after the bridge amplitude, that's this here, grows very large, and whilst the bridge amplitude is small. Then we added this feedback to the model, and the feedback is I change how often I put my foot, or I change how far forwards I put my foot, depending on how wide I'm putting my feet. If you include that feedback, then something really interesting happens. You do see a large degree of coherence, at least, or a change in the order parameter, apparent synchronization. This is, if you like, 20% of the pedestrians appear to be walking in step. But notice this happens as a result of the instability. The damping coefficient goes negative, the amplitude increases, and then as the amplitude increases, that causes more of this, what's sometimes called phase pulling or coherence amongst the pedestrians. You can also plot the, here I'm plotting the bridge frequency dividing by the pedestrian frequency, and here I'm plotting the damping coefficient. And what you find is that this damping coefficient can actually sometimes, this is the amount of damping per pedestrian, or the amount of negative damping per pedestrian, that actually it's frequency dependent. It's a question of timing. What I was saying about putting your foot out wide and putting your foot out was kind of assuming that I'm walking at a similar pace to the bridge is oscillating. If the bridge is oscillating much faster or much slower, then actually during the time that I'm on my right foot, the bridge might have moved back. And so there's an element of timing. So it is frequency dependent, but what we find here is that between a frequency ratio of 0.8 and 2 of the bridge frequency to the pedestrian frequency, the bridge is liable to this instability because these curves are positive. These three different curves are for different pedestrian frequencies. See, I'm plotting this just as a ratio. It isn't actually only a function of this ratio. It depends on the underlying pedestrian or bridge frequency. The blue curve is an analytic curve which you can derive from the simple model, and this here is in simulations the number of pedestrians it took to make the bridge go unstable. So if there's this large frequency mismatch, you can never make it go unstable. These are violin plots that show you a big scatter because there's a scatter depending on all kinds of variations that are here. But essentially, you do not have to be in this regime where there's a one-to-one ratio between the bridge and the pedestrian frequency. And in fact, that's not optimal. About 1.3 or 1.4 ratio, well, optimal in the sense of trying to trigger the instability. The worst case seems to be around 1.4 as the ratio between the bridge frequency and the pedestrian frequency. Then it only takes about 150 pedestrians for these parameters. And we could do the same for the falling over model, the Bellick et al. Model that I mentioned. And this one also shows a very large amount of coherence. This one does synchronize and already been used as an example of synchronization. But once again, synchronization happens after the instability. The instability where the negative damping first kicks in occurs at 156 pedestrians. And then at least for these simulations where we're adding the pedestrians slowly, it took a little bit later before the amplitude saturated. And the amplitude saturates as the pedestrians now all start to fall into sync. You see, prior to the instability, they all have random phases. I'm plotting a sample, at least, of the pedestrians as sine waves, but here most of their sine waves all lie on top of each other. And we can do a similar thing and find, sorry, something's got chopped off here, this damping coefficient and the number of pedestrians. So, 2 slides, almost there. Direct conclusions. Partial synchronization, this 20% of pedestrians might synchronize, probably is a property of pedestrians on laterally excited bridges, on laterally moving bridges. So it probably is a thing. It's not a bad theory. But I claim it doesn't explain the instability. It doesn't have explanatory power. It's an observation of what happens. It doesn't explain why it happens. And in particular, pedestrians are not like Huygens clocks, and the bridge is not a passive coupling device. It has its own natural frequency. It's not like the pedestrians are choosing to synchronize on their average frequency. And it requires therefore, the pedestrian walking frequencies to be tuned to the frequency of the bridge, and it also gives no insight to the engineers on how to measure the critical number of pedestrians in order to have a safe bridge. This concept of negative damping, I claim, is intuitive. It's basically what I do in order to not fall over when I'm walking on moving ground. What I'm doing is I'm giving energy to the bridge to stop myself having too much energy in the lateral direction. This effect can be measured. You can measure it. Arup measured it. You can model it, and you can use it as part of a simulation. It's robust to the choice of mathematical model. We took 3 different mathematical models and they all showed this negative damping, and the negative damping showed when the numerical simulations go unstable. It explains instability across a wide range of bridge frequencies. It's not just tuned to the idea that the pedestrians have to be walking at the bridge frequency, or indeed that they have to be walking at similar frequencies to each other. And it gives the engineer a way to compute this critical number of pedestrians, and there's a NOR there which should say and the necessary bridge damping to avoid instability. So in a sense, the engineers were right all along. All this hoo-ha, all this stuff about saying, wow, what a great example of synchronization, it probably isn't. There was probably some synchrony, but actually at large amplitude there always is some synchrony. But it was probably more like these cats that I have here, in that there was precious little synchrony going on. But that's not the point. The point is, it's this negative damping criterion, which is something you can calculate, is nowhere near as famous. It has 30 citations, whereas the Nature paper on synchronization has several hundred, maybe 1,000, I'm not sure. It's been there in the engineering literature for a long time. It's just an inconvenient truth. It's if you like, if I can be a bit more philosophical, the synchronization of near-identical oscillators is a great mathematical theory. It explains all kinds of things, but it doesn't explain everything. And in my view, it doesn't explain why, and it doesn't predict when bridges go unstable to lateral oscillations. So maybe this is a case of what Thomas Huxley described as the great tragedy of science, the slaying of a beautiful hypothesis by an ugly fact. But maybe not. Maybe actually it's a failure to apply the core principle of mathematical modeling, which is Occam's razor. If there exist two explanations for an occurrence, the one that requires the smallest number of assumptions is usually correct. Sometimes we go out there with our hammers as mathematicians, looking for nails and saying, oh, I'm an expert in synchrony. Oh, look, there's a perfect example of synchrony, without actually checking the assumptions, without saying, what is truly oscillating here? What are truly the natural frequencies, etc.? Or if you like, keep it simple, stupid. If I've learned anything as a mathematical modeler, I almost never make progress or have insights by making something more complicated. It's nearly always the case that the truth is much simpler than you think. You just haven't been looking at it the right way. And avoid the wisdom of the crowd. Popular explanations are often wrong. There's a physics textbook explanation. There's another bridge instability, very famous in physics and engineering textbooks and calculus textbooks, that says that this is an example of resonance, where the wind started resonating or the vortices shed from the cables of a bridge resonated with the bridge's natural frequency, balderdash. Or some of the popular explanations you see of how aeroplanes generate lift, or even explanations I've seen for why there is a Nobel Prize for economics, there isn't, and why there was never one for maths, which has nothing to do with Nobel and Mittag-Leffler and their personal relationship, or otherwise. So finally then, if I can give you some messages, it's think. Never be afraid to think for yourself. Be a little bit scientifically stubborn. Don't follow the wisdom of the crowd. Don't say just because everybody else says it's an example of one of these. Find out for yourself. Question. Check the assumptions. Apply Occam's razor. What actually are the hidden assumptions am I doing here? Am I making this problem more complicated than I need to? And sometimes we do that. And I think mathematics is a very good tool for cutting out assumptions and making things simpler if we only did it the right way. And so finally then, I'd like you to remember that rhythmic clapping without being presumptuous, and thank you very much.